All right, so for lesson 60, like I said, in the middle of page 244, it says the volume of prisms and cylinders. You can find that by, it's equal to the area of the base times the height. What do we mean by the base? What's the base? Come on, guys. You know what the base is. Huh? The bottom. Yes, the bottom of it, right? It's actually, because these are, because these particular figures are at 90-degree angles to the bottom and the top, so it's also the area of the top. You could think of it like that. The base is either the bottom or the top. There's actually a picture, if you go to the page 243, you see that right prism on the top right, and also the right cylinder that's on the bottom right. Notice the base is both labeled as the top and the bottom, right? Because for these figures, the shape on the top and the bottom is going to be exactly the same, right? So if you're finding the volume of a prism or a cylinder, it's equal to the area of the base times the height. So we have a figure listed in example 60.1 on page 244, and I'm not going to try to draw that figure because you guys would laugh at me and I'm going to cry on camera. So I'm just going to let you look at the picture in the book. All right, does everybody have their book? Liliana does not have her book. Mm-hmm. Could you just show her a picture there, Hannah, so she knows what we're looking at there? Oh, that's so sweet. Look at the sharing going on. Thank you so much, Hannah. So that's the figure we're trying to find the volume of, and they tell us that the area, they give us the area here, we don't even have to figure it out. They tell us that the area of the base, I don't think that's my marker, it's not. They tell us that the area of the base is 28 square centimeters. So we'll just write that down. Area of the base is 28 square centimeters, and they tell us that the length of a lateral edge is 10 centimeters. Now they're trying to mess with us to make sure we know what the length of a lateral edge is. What do we translate that to mean as we're considering this figure here? What is the length of a lateral edge? When in a figure like this, when it's talking about the lateral surface, it's talking about the side. All right. So like if this marker here was a cylinder, all right, and we're saying, and so the base we said is the bottom and the top, right? The lateral part of this marker would be the area around it, all right? So like for example, if they asked us to find the lateral surface area, we're just finding the area around here, not including the base and height. So would they tell us what the lateral, the length of the lateral edge is? What are they actually telling us? If this is the lateral edge, they're telling us the height of the figure. You guys see that? So they're trying not to be too obvious. But what they're really giving us is they're giving us the area and they're giving us the height. All right. So they tell us that the height is 10 centimeters. And so we're told by our definition that the volume then is the area of the base times the height. So to find the volume of this, we're just going to multiply 28 centimeters squared times 10 centimeters. And that's going to be equal to 280. And since we've got centimeters squared times centimeters, what would our units be for that? Centimeters cubed, right? Cubic centimeters. So your volume measurements will always be cubed. If you're ever unsure with that, if everything's in meters or everything's in inches, if you know it's volume that you're finding, it'll always be cubed. If it's area that you're finding, what will the value of the unit always be? It'll be that unit what? If it's area, it'll be that unit squared, right? All right, so, oh look, the next thing is the lateral surface area. So that's the next thing that they want us to find. So it's good that we just talked about that. So the lateral surface area, any questions about this? That's about as simple as straightforward as it gets, right? As long as they give us those values right out, it's really easy to just multiply them together. Eventually we're going to be finding the area of the base ourselves. But it tells us that the lateral surface area of a right prism or a right cylinder is equal to the perimeter of a base times the height. So when you talk about lateral surface area, I'm going to just write our two formulas from this chapter. The volume is the area of the base for these types of figures. The area of the base times the height, and the lateral surface area, which I'm just going to abbreviate as LSA. All right, lateral surface area is equal to the perimeter of the base times the height. All right, so one we need the area of the base, the other one we need the perimeter of the base. Okay? So it says find the lateral surface area of this right prism whose bases are regular pentagons. Dimensions are in meters. So we got, maybe I could do this one. Let's see if I can draw this one. Whoops, already messed up. Yeah, if you remind like way too tall. There. Then you come down. Here. Like this. There. Here. And then we gotta go across here. There we go. Not terrible. Could be worse, right? It's not great either, but anyway, you get the gist of what the shape looks like. And so this is 15, and they tell us that this is 8. And there's another important part to this problem. We've got to find the we've got to find the perimeter of this base down here. What do I need in order to find the perimeter? How do you find the perimeter of a figure? Of any polygon, which that's what this shape is. A pentagon is a polygon, right? It looks like this. It's 5-sided. What do I need to know in order to find the perimeter of that? I need to know the length of all the sides, right? And they've only got one side labeled on this figure. But they give us a clue in the way that the question is asked. And they said, find the lateral surface area of this right prism whose bases are regular pentagons. So we have to remember what the term regular means. What does regular mean for any polygon? Do you remember? I don't even remember. I know I've talked about this in geometry this year. I don't remember if we specifically discussed this. Probably somewhere at the very beginning of the year they threw that in. When it says regular, it means all of the sides have the same length. Okay? So a regular regular polygon, all sides have same length. And all angles are the same. So the angles don't really matter to us this time, but just so you know, if it's regular, we use the little tick marks there to identify the fact that they're all equal to the same length, and we could use this little symbol here with the angles to say that all the angles are the same. I really didn't draw this one to where that is the case, but a regular one is like that. Okay, I should have slanted these sides in, and it was all the same. All right, but that's what regular means. And so since that's the case, then that means this side is also 8, this side is 8, this side is 8, and this side is 8. Does that make sense? So if we want to find the perimeter of the base of this guy, which we're going to have to find the lateral surface area, then we just add up 8 5 times, right? So perimeter of the base equals 8 plus 8 plus 8 plus 8 plus 8. And so that's 8 times 5, so this is going to be 40. What was our units? Was it centimeters? Oh, meters. So this would be 40 meters when we add all those up. All right. And then what's the last thing we have to do to find the lateral surface area? What's our formula say? So we got to multiply it times the height, right? So that's the last step. Lateral surface area equals the perimeter we just found, which is 40 meters, times the height, which is 15 meters. So when we multiply those two together, we get 600. And this is an area. It's lateral surface area, so what will our units be? If it's an area. Square units, right? Who said that? Is that you, Liam? Okay. Bob? Liam, this week only Bob. All right. Does that make sense? Now again, what is the lateral surface area? We're just trying to find the area around the outside here, right? So if you think about it with this figure, they've got a drawing in the book where when you kind of consider the lateral surface area, think of taking the figure apart and laying it out flat. All right? So this figure here, if we took it and laid it out flat, do you guys see that it would form that it would be like that? You would have 5 sections here, 5 rectangles, each with 15 meters with the height, and each of these values here would be 8, right? And so this whole distance here is 40 meters, and so that's why the lateral surface area, if you do it like that, you realize all I'm really doing is figuring out the area of a rectangle, right? And the area of a rectangle is the length times the height, right? Or the length times the width, or however you want to think about it. So that's all we're doing. The perimeter of the base will be the area of the rectangle, will be the length of the rectangle when you unfold the figure, okay? So you can either think about it like this. This is how I tend to think about it. So then no matter what figure they give me down here, I always know, okay, as I unfold this, I got to find the perimeter around the outside there, and that's going to be my length on this. You can think about it like that, or you can just remember these formulas, right? At a minimum, make sure you remember those formulas, because that's really all you need to know in order to do these problems. Okay? Any questions about any of that? You guys good? All right, excellent. Let's move on to lesson 61. Subsets and subsets of the set of real numbers. So they've got a chart here on, it's at the bottom of page 249, and they tell us what real numbers encompass. So you'll see me, when I'm talking about a real number, I'll abbreviate that with an R with like a double line on the left side here. Picked that up somewhere in math years ago, and that symbol is, like in here, I think they do it a little bit differently. Let's see if I see the symbol.
They have not a Z.
Is that what they use for reals though? They use that for integers. Yeah, so they got natural numbers, which is an N, and whole numbers, which is a W. Oh, here it is. Oh, they do kind of do it like that. So look in the middle of page 241, right next to 61B. Where it says subset of the set of real numbers. You see the symbol R? It's in that first paragraph right in the middle of the page. So theirs looks almost like mine, except they kind of connect this down at the bottom. You guys see that? So anyway, if you see me draw R with the double line on the left there, I'm just abbreviating real. That stands for real numbers, okay? And what are the real numbers? Well, the real numbers include, so they've got this table down at the bottom here, and it includes our irrational numbers. And irrational numbers are any numbers with, it's numbers that cannot be expressed as the fraction of 2 integers. So it's anything with a square root or a cube root, so it has a root that can't be simplified. Or a repeating non-repeating decimal. So in this case, it would be, they give us examples like square root of 2, cube root of 5, pi, because it's just it just goes on and on, never repeats. Like you can't, if we had this, if we have 1/3, 1/3 is a repeating decimal, but we can express it as the 3's are repeating, so we can put a line over that just so there's the 3's go on and on. But with pi, you don't have any repetition like that. And so we can't express pi as a fraction like we can here. So irrational numbers would be over here. Those are actually considered real numbers. And then also rational numbers would be included in that, which is our numbers that can be expressed as a fraction. Numbers that can be expressed as a fraction of whole numbers. And then included in this idea of rational numbers is the concept of integers. And so integers would be a whole number, but from negative infinity to positive infinity, so -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. Right? Those would be the integers. And then within the integers, you have whole numbers. And that would be 0, 1, 2, 3, 4, and that goes on and on. So just the positive integers, including 0. And then finally, we have natural down here. I'm running out of room here. Natural or counting numbers. And that's, we usually start counting with 1, so that's 1, 2, 3, 4, dot, dot, dot. All right? Unless you're a computer programmer and we count starting at 0. So we actually count with the whole numbers. But that's how we learn to count, right? Starting with 1. So this let me close off my box here. This box here represents all real numbers. Everything inside that box would be included in this idea of real numbers, all right? And then boxes within one another. Natural numbers are part of the rational numbers. Whole numbers are part of the natural numbers, rational numbers. Natural are part of the whole numbers, and so forth, right? Does that make sense to you guys? Just kind of summarizing all that, how those numbers fit together. And so they do have symbols for something, like for integers, they use this symbol Z, where they do like a double line in the middle of the Z. So that's what Z looks like. They just use W and N, which is interesting because I thought I had seen in another Saxon book that they actually kind of use that double thing for the W and the N for natural numbers, but they don't do that in here, so we'll stay away from that. So this would just be represented by W. This would just be represented by capital N. And so they ask us some questions here. They say, we have to remember our symbols that we learned. Where was that? That was a couple of chapters back, when we learned symbols like this. Where was the chapter where we learned that? You guys remember? We can see a list of all of those. Sorry, I should have looked this up before. So we'll just have that right in front of us. So in 56, that's where we learned this symbol, actually. that, and we learned that with a slash through it, right? So it's either it's part of a set or it's not part of a set. I thought we learned some of these other ones as well, but maybe not. Maybe these symbols are new. They're just letting us know about those here. So
Where's the notice from the geometry? Instead of the line in between those, we would have the end. I have no idea what that's called, but
in geometry, I was just teaching some class. It might have been my pre-algebra class where we had like a big list of symbols because we're a little further along in the book. So maybe this is first introduced to you in geometry. So have we seen, like they noted here, that if we talk about a set of numbers. So like this would be a set of numbers, and we've already done some problems with that. Some of you, we just had a quiz or a test. I remember because somebody had left these off. Curly braces. Anytime you designate a set, you put the curly braces around the outside. That's what identifies it as being a set. But if we do the curly braces without anything between it, this is the empty set. And then this right here is the null set, which just means it doesn't contain any numbers. So that refers to the null set. And this symbol here. So this means it's a member of the set. This right here means subset. So if we're given a set like in example 61.1, we have these sets here. D equals 0, 1, 2. And then E equals 1, 2, 3, ... And then G equals 1, 3, 5. It says, whoops, should have been a curly brace. So what the problem says to do is tell which of the following assertions are true and which are false and why. And so the first one that they give us is E is a subset of G. Is E a subset of G? So this means subset. Is E a subset of G? What does that mean to be a subset? It means is everything in E also contained in G? Is E a part of G? Are all of the numbers in E contained within G? Is that true? They're not, right? Clearly that is not the case. So this one would be false, right? It goes from 1, 2, 3 all the way to infinity, and so G only contains 3 numbers, so there's no way that G could contain E. So that will be false. That makes sense? You have a question about that?
I'm looking at page 56, and it's the exact same thing.
Page 56? Or lesson 56?
Lesson 56.
Okay. So
I've
we have used that symbol before?
We have, and it was for the true or false question.
Okay, I thought we had seen it, and so in lesson 56, is there a...
There was a question on either 58 or 59.
Yeah, okay.
When you open it up. 7.
Yeah, so this is a member of, it's very similar, except the symbols here look like this, right? So this means member of. And this means not member of. But this is a very similar idea, right? If it's a subset, it's a smaller portion of the bigger set. So you really think about those the same way. All right, so the next one they give us is G, a subset of E. So let's reverse what we just had. And is that true? Is this set a subset of this set? It is, right? 1, 3, and 5 are all that G are comprised of, and 1, 3, and 5 can be found in E. So we would say this one is true, right? And then finally, is D a subset of E? So they really hard to not make those look like C's when you draw it. Is D a subset of E? I see a yes and I see a no. Which one is it? How many people say yes? How many people say no? Why is no correct? It's close. Is everything in D contained in E? What's E missing that's in D? The 0. You see that? Right? So because this one started with 0 and this one does not start with 0, then it would not be a subset. So this would be false as well. All right? Is that clear to everybody? All right, let's so now we're going to have a question that involves all of this stuff here and making sure that we understand how these values are organized inside the real number set. And so it says 1/2 is a member of what subsets of real, I'm going to abbreviate real, like I said I would. What subsets of reals? All right? So 1/2, where does 1/2 fit? If we look at all the stuff that's included in real numbers, where could we put 1/2? Which of these, 1, 2, 3, 4, 5, and we're going to count the entire real as well, which of those would 1/2 fit in? For example, could 1/2 be counted as a natural or counting number? This down here. Did you guys learn to count that way? No. 1, 2, 3, that's what the counting numbers are. So 1/2 is not part of that. Does that make sense? Is it a part of the whole numbers? No. Is it a part of integers? No. Is it a part of rational numbers? Yes, right? So we would say the subsets that this is a part of is rational numbers. Is it a part of irrational numbers? No, because it has a terminating decimal value, right? It can be expressed as a fraction of whole numbers. This cannot. Let's see, irrational numbers, root that can't be simplified, or non-repeating decimal, i.e., can't be expressed as a fraction of whole numbers. So if it can be written as a fraction, it can't be an irrational number. All right, so 1/2 would be included in the rational numbers, and then it would also be included in the reals. It's in the general real number category. All right? What about the number 5? What subsets of real numbers would you include 5 in? You guys got to give me some feedback. We got only Cohen and Bob on board.
Natural or counting, I think.
Natural, counting, or natural or counting, right? So we'll write that as an N. It is included in the whole numbers. What about the integers? Yep, it's included in the integers. So we'll write that as that Z with the double line. What about in rational numbers? It is, right? You can express that as a fraction. We could write 5 as 5 over 1. So it would be included in the rational numbers. And then finally, it wouldn't be irrational, right? It can't be in rational and irrational. Does everybody see that? It's either one or the other as far as those go. And since it's in one of these categories, then reals would always be the answer for this as well. Okay? And then finally, 3 square root of 2. Can we simplify out that square root? Like if it was 3 square root of 4, we could simplify that to be 3 times 2, so this would just be 6, right? But can we do that with this? Can we get rid of that square root? We can't, so that puts us immediately over here in the irrational numbers part. And if it's in the irrational numbers part, it can't be any of these guys. right? So this one here would be part of the irrationals, which would mean that it also has to be part of the reals. Does that make sense to everybody? We're just learning to categorize these, okay? Yep.
What would not be a part of the real number? It's just like no number at all.
A real number?
Well,
The imaginaries, what I mentioned earlier, we haven't learned about yet, right? So basically every number that you know about so far would be a real number, okay? All right, any other questions? All right, well, we talked about cube roots and square roots and earlier, and so we're going to move on and talk about those in a little greater detail. I'll leave this stuff on the board here, because that's all important stuff for your homework. So we have a definition of a square root. The square root is technically this. If x is greater than 0, right? We said that in when we were doing that one problem that you asked about at the beginning, Ada. If you're taking the square root, if you're taking any even root, square root, fourth root, sixth root, it's got to be greater than 0. If x is greater than 0, then the square root of x is the unique positive real number such that the square root of x squared equals x. So they're just giving us a formal definition of it. Hopefully, you guys already know that if I have like the square root of 3 and I take the square, if I square the square root of 3, what do I get? Maybe you haven't really focused on this that much. Based on this definition right here, what would the answer to that have to be? I didn't get Ada before. Sorry, Ada. If this is true, if the square root of x squared equals x, what does the square root of 3 squared have to equal? 3. It has to be 3, right? You guys see that? Is that you, Jonah? Yeah. All right. It has to equal 3. So the way I think about it in my mind is that square undoes square root, and square root undoes square. All right, they're kind of like multiplication and division go together. One undoes the other, or addition and subtraction. One undoes the other. So just like this is true, if I were to take the square root of 3 squared, then that also equals 3. Okay? So when you're doing algebra problems, that's important to understand. You need to recognize that one undoes the other. So if you're confused about that, I would highly recommend just looking up, going to Khan Academy and just looking up working with square roots and get some practice on that if that's still an area that you're kind of fuzzy, all right? But we first want to make sure that we know how to do this on our calculator, and so they ask us to determine the square root of 18, all right? So everybody that has their calculator with them, make sure that you can go into your calculator and take the square root of 18. Make sure that we can get that value. So when I do that, I get, if I round it to, does it tell how it says, determine it to 5 decimal places. So when I round to 5 decimal places, I get 4.24264. So make sure when you punch that in your calculator, you get the same thing. Is everybody able to get that? Anybody not get that? Let me ask you that way. You guys just stare back. Oh no. Did you get it now? All right, now we got it. Cool. Everybody got it. Use a calculator to determine the 2 square roots of 10 to 6 decimal places. So what does that mean? This has to do with the fact that we have to understand this is true. If I take the square root of 9, who knows what the square root of 9 is? 3. Well, when you take the square root of 9, you're asking the question, what number multiplied times itself will equal the 9, right? And the number that multiplied times itself will equal 9 is 3, right? But we need to also recognize that there's another number that when multiplied times itself will equal 9. Does anybody know what it is? Three times itself will equal 9. But isn't it also true that negative 3 times itself will also equal 9? So technically, when you're taking the square root of a positive number, there are 2 possibilities. There's a negative and a positive version. All right, there are a negative and positive options. And so that when normally if they just say find the square root of 18, we're just looking for the positive value. Yep.
Will the calculator ever give you negative?
It won't. It'll always give you the positive one. So you need to recognize that it's true that there's the negative version as well. The negative will always be the same number, but just with the negative sign in front of it. Okay? So a minute ago when we just got when we got this, it's also true that negative 4.24264 would be a solution to square root of 18. Okay? So normally we just default to the positive, but here in this problem they actually ask us to determine the 2 square roots of 10 to 6 decimal places. So I punch in 10 in my calculator. I punch in the square root of 10 in my calculator, and I get 3.1623. Since it asked me for both square roots, I'm going to list the negative version of that as well, as negative 3.162. They asked us to go to 6 decimal places, and I went 4 like last time. But does that make sense to everybody? Okay. What about example 62.3? It says, without using a calculator, write the squares of the counting numbers 1 through 20. All right? And so they're wanting us to just memorize this. They suggest that you memorize 1 to 15. So I will confess to you, I have not memorized square roots 1 to 15. But let's see how high we can get. All right. So 1 squared, 2, 3. Let's see how high we can get without looking at our book. All right, 1 squared. You guys better know this one. 1, right? 2 squared. I heard a 4. 3 squared? 9. 4 squared?
16.
What's next?
45.
Yep.
36.
36. 49. Right now we're still in our times tables, right? 9 times 9 is 81. 10 squared is 100. 11. 121, that's right. What about 12? 144. 13, this is where it starts getting shaky. 169. Did you just have that one memorized? Did you? What about 14? What is it, 196? This one I did not remember. And then what's 15? Is it 225? Or is that that's 5 cubed, isn't it? It is 225. All right, cool. 225. So they recommend that you at least memorize it to that. All right, it's just going to help you solve some of these problems. It's going to help you recognize when you have perfect squares underneath the square root if you know these. So I'm almost there. I just need to work on these last 2. All right. But that would be helpful. they go all the way to 20, and 16 is 256, 17 is 289, 18 squared is 324, 19 is 361, and 20 is 400. 20 I could do, but yeah, from 16, basically from 14 to 19, I'm in trouble. All right, so what about, let's see if we could do this. Without using a calculator, determine between what two consecutive integers the square root of 10 lies. So again, this has to do with us being able to estimate. When we don't have a calculator handy and we're trying to estimate roughly what a number is, you're going to need to be able to figure out what square root of 10 lies between. And so what two integers would square root of 10 be between? Now what do we mean by integers? Look over there. What are integers? Negative numbers without a decimal from negative infinity, right? So we're starting up, I'm not going to start at negative infinity. You're welcome. But I'm going to start at negative 5, negative 5, negative 4, negative 3, negative 2, negative 1. Keep going to positive 0, 1, 2, 3, 4, 5, and so on to infinity. Those would be integers, right? So what are the two integers that negative 10 is between, I'm sorry, the square root of 10 is between? How are we going to figure that out? The square root of 10? Well, that's what we're trying to estimate. We don't have calculators. So 10 is not a perfect square, right? So what numbers are perfect squares that are sort of just before 10 and just after 10? 8's not a perfect square. 9 is, right? So do you guys see that the square root of 9, that number is smaller than the square root of 10. What would be the perfect square that's greater than 10? We just did it over here, right? The square root of 9 is 3. The square root of 16 is 4. Do you guys see that? You guys do realize this, right? Because this is true, that means the square root of 1 equals 1. The square root of 4 equals 2. The square root of 9 equals 3. The square root of 16 equals 4. That's part of why these are helpful to have memorized, because then you also know what the square root is of the perfect square. Okay? So does everybody see that? That since 9 is less than 10 and 16 is greater than 10, 10's got to be square root of 10 has to be somewhere between the square root of 9 and the square root of 16. You guys see that? So what is the square root of 9? 3, right? Who said that? All right. That's all it takes. It's just a little kind of, even if it's just a, all right, that's enough. It's enough to get your name on the board. If you guys even did the little, if you did that, I'd put your name on the board for that, all right? It's because you participated. All right, so 3, square root of 9 is 3. And then the square root of 16 is 4, right? So we know then that the square root of 10 lies somewhere between 3 and 4. You guys see how you could estimate that? And so if you punch it in on your calculator, what do you actually get for the square root of 10? Let's see if we were right. I got 3.16. All right, so sure enough, it's in between 3 and 4. So 3 and 4 would be the two integers that satisfy, that answer this question here. Okay, does that make sense to everybody? You guys see how you can do that? And when that's important, like in geometry, for example, I'll give my geometry students a list of sides for a triangle, and they have to construct the triangle and tell me whether or not it's a right triangle, an acute triangle, or an obtuse triangle. And in order to do that, you have to be able to figure out which side is the longest side. And so if I'm giving you something like square root of 15, 2 square root of 2, and square root of 7 as your sides, you got to know which of those is the bigger number, because that's the one that you're going to, if it was a right angle, you're going to assume would be your hypotenuse at the right angle from the right triangle. And so in this case here, you'd have to be able to figure out the square root of 15 is bigger than 2 square root of 2. But this is actually the biggest number out of all of those. All right, so estimating square roots is helpful and stuff like that. All right, let's move on to the latter part of this chapter and make sure we can finish this lesson out. Just got a little bit more. And this one says, making sure that we understand the cube root. Now, I've already we've already done one of those, and so the basic definition, we started the class with that. The basic definition of cube root is, whoops, I didn't mean to do that. I meant to do cube root of x cubed. The definition says that if I take the cube root of x and then I cube that whole thing, I'm going to get x, right? So I need to understand if I do the cube root of 44 and I cube that, that's going to be equal to 44, all right? Just like square undoes square root and vice versa, cube undoes cube root, vice versa. Yes?
I was going to ask the question, but answer that.
Okay, all right. Does that make sense? So make sure that you recognize that. It's the same way with the fourth root. They've got a definition up at the top of page 255, which says the same thing with fourth root. But what that means is that, I mean, you need to understand that the cube root of 8, what does that mean? With the cube root of 8, we're asking the question, what number can I multiply by itself 3 times and get the number 8? And the number that I can do that with is 2, because 2 times 2 times 2 equals 8. Yep.
Would they ever stick a negative on it?
In the cube, they could, right? Because with the cube, if I multiply -2 times -2 times -2, I'll get -8, right? So if there's a negative sign underneath the cube root, then your answer will have a negative sign, all right? If it's positive, then your answer will be positive. And then for the fourth root of 16, we're asking what number can we multiply by itself 4 times and get 16? And the number that we would do that with is 2 times 2 times 2 times 2. Again, you can use your calculator to calculate this. Your calculator will help you out with that. But it needs to make sense too, all right? So the final thing that they show us is we need to recognize if we have an algebraic equation, and that algebraic equation is this. It gets simplified down to x squared equals 4. How do I get to that x? Because remember, to solve the equation for the variable, you've got to get the variable all by itself, right? So based on what we've learned today about the way that square roots undo squares and vice versa, how would I get to that x there? How would I get the x by itself? I would take the square root. Does everybody see that? Because if I take the square root of x squared, I'm left with just x. But whatever you do to one side in algebra, you have to do to the other side in algebra. So I have to take the square root of 4, right? But remember, when I take the square root, what we said earlier, there are technically 2 answers. So it would be plus or minus the square root of 4, so the answer here would be plus or minus 2. Either a positive 2 or a negative 2 would satisfy that equation, and both answers are valid. All right, so we need to make sure that we recognize that either of those would be true. So there's some examples you can work this week and practice that, and you guys got 2 weeks, right? So enjoy your break, and come back with any questions that you have, and study your practice so we can take a short quiz over our practice next week. Yes?
How will you